Today mobile phones are part of our lives. Over the last 2 decades there have been many revolutions and developments in mobile networks. Each generation of mobile network brought a specific change to the society. The first generation gave us the first analog cell phones. In the second generation new features like SMS and voicemail were added to the mobile handsets. The third generation brought higher data transfer rates, enable mobile web browsing, image sharing and GPS location tracking. Fourth generation made our phones smart with broadband deep web functionality, delivering the speed that we enjoy today. If we look at the statistics of mobile trends from year 2015 to 2021, the figures will amaze us. The number of smartphone users in India was estimated to reach over 760 million in 2021. As of 2020, the average data consumption per user per month across 3G and 4G networks in India was at 13,462 megabytes. A study highlighted that by the end of 2019, India had 200 to 250 million IoT-connected devices. So what does this statistics tell us? This statistics alarms us about the demand of more bandwidth, more reliable service, and most important faster data speeds. The next generation of wireless networks, 5G, promises to deliver that, and much more. With 5G, users should be able to download a high-definition film in under a second, a task that could take 10 minutes on 4G LTE. Researchers say these networks will boost the development of other new technologies too, such as autonomous vehicles, virtual reality, and the Internet of Things. So what exactly is 5G? It's not yet clear which technologies will do the most for 5G in the long run, but a few technologies have emerged. Which includes millimeter waves, small cells, massive MIMO, full duplex, and beamforming. Now let's look at the first technology. The millimeter waves. Today's wireless networks have run into a problem. More people and devices are consuming more data than ever before, but it remains crammed on the same bands of the radio frequency spectrum that mobile providers have always used. That means less bandwidth for everyone, causing slower service and more dropped connections. So the problem of global bandwidth shortage has motivated the exploration of the underutilized millimeter wave frequency spectrum for future broadband cellular communication networks. This new spectrum of frequencies, the millimeter waves, use higher frequencies than the radio waves that have long been used for mobile phones. Millimeter wave carrier frequencies allow for larger bandwidth allocations, which translate directly to greatly increased data capacity, while the latency for digital traffic is greatly decreased, thus supporting much better internet-based access and applications that require minimal latency. Millimeter waves are broadcast at frequencies between 30 and 300 GHz. They are called millimeter waves because they vary in length from 1 to 10 millimeters, compared to the radio waves that serve today's smartphones, which measure tens of centimeters in length. Although the available bandwidth of millimeter wave is promising, the propagation characteristics are significantly different from radio frequency bands. Millimeter waves suffers large diffraction and blockage from buildings and other obstacles. They suffer rain attenuation, atmospheric absorption, and foliage loss behaviors. To get out of this problem, we need the second technology. Small cells. In the traditional mobile communication systems, each transmitter, typically called a base station, covers a certain area, called a cell. While a cell can cover a larger area under a light load, it shrinks if the load increases. The reason for this is the growing number of users, as they remain crammed on the same bands of the radio frequency spectrum. Therefore, less bandwidth for a large number of users may result in slower and dropped connections. Also, if we use millimeter waves for higher bandwidth, we know millimeter waves suffers high path loss and can be absorbed by the obstacles. This problem of traditional mobile communication systems can be overcome by increasing number of base stations that require minimal power to operate and can be placed every 250 meters or so throughout cities. These base stations are called small cells in 5G. This can be very useful in dense areas like cities, where if a user moves behind an obstacle, his device switches to a new base station, allowing him to keep his connection. Having more stations means the frequencies that one station uses to connect with devices in one area can be reused by another station in a different area to serve another customer. Technology number 3. Massive MIMO. 4G base stations have a dozen ports or antennas to handle all cellular traffic. In 5G base stations will have about 100 ports, which means many more antennas can fit on a single array. which means a base station could send and receive signals from many more users at once, increasing the capacity of mobile networks. This technology is called massive MIMO, which stands for multiple input multiple output. Massive MIMO looks very promising for the future of 5G. However, installing so many more antennas to handle cellular traffic also causes more interference if those signals cross. That's why 5G stations must incorporate beamforming. Technology number 4. Beamforming. In the previous generations of mobile communication, the signal was broadcasted in all directions from an isotropic antenna, resulting in more interference of the signals. Beamforming helps by focusing a signal in a concentrated beam, just like the beam of our ship's searchlight or beam of a laser, that points only in the direction of a user, rather than broadcasting in many directions at once. This approach can have a number of benefits like a focused beam towards a user, less transmit power with strong received signal and less interference. Beamforming technique achieves this by placing multiple antennas in close proximity, all broadcasting the same signal at slightly different times. The overlapping waves will produce interference that in some areas is constructive, it makes the signal stronger, and in other areas is destructive, it makes the signal weaker or undetectable. If executed correctly, this beamforming process can focus your signal where you want it to go. Besides boosting data rates by broadcasting over millimeter waves and beefing up spectrum efficiency with massive MIMO, wireless engineers are also trying to achieve the high throughput and low latency required for 5G through a technology called full duplex. Technology number 5. Full duplex. The means to provide two independent channels or two-way communications is called duplexing. There are two distinct methods to achieve duplexing: FDD and TDD. In FDD, two different carrier frequencies, one from each band, are assigned to a user, one carrier frequency for transmission from the user called uplink, and one carrier frequency or reception by the user also called downlink. In TDD, time rather than frequency is used to separate the transmission and reception of the signals, and thus a single frequency is assigned to a user for both directions uplink and downlink. In half-duplex, transmission is bidirectional, but only in one direction at a time. The end devices can both transmit and receive, but not at the same time. In half-duplex mode, the entire capacity of the channel is taken over by whichever of the two devices is transmitting at the time. Examples of half-duplex communication are walkie-talkies or cars running on one-way lane. In full duplex mode, transmission is simultaneously bidirectional. The end devices can transmit and receive simultaneously over the same frequency band, providing the potential of doubling the capacity compared to conventional half-duplex systems and sustaining the evolution of the fifth generation, 5G, technologies within limited spectrum. With these and other 5G technologies, 5G promises ultra-low latency and record-breaking data speeds for consumers. Ultra-fast 5G service could revolutionize the world that we live in today.